All right, guys. Can you guys hear me?
Yes.
All right. So let's get started. So welcome to our boot. This is like our knowledge-based lecture. Okay. So we have like some students who was actually joining us in the boot camp. If we do comparison between the boot camp lectures and our knowledge-based lectures, the boot camp was kind of like we have very like the high density, right? It's very concentrated. We only have like 10 lectures. We like to pretty much cover everything. However, whenever we go to our knowledge-based lectures, we're kind of doing more detailed, in-depth explanations. We're trying to cover one or two topics in 10 lectures. So for instance, in our current session, we're going to be talking about the sequence and proving strategies for the discrete math. So that being said, in our current lectures, we have like kind of like a small scale talking about our students, our classes, and we have more chances for the interactions. So therefore, during the lecture, if you have any questions, just let me know. I want to have as much interaction as possible. I'm going to be asking questions for different students. You can reply me. Either you can just basically like Andrew, you can just unmute yourself, then talk to me, which is the preferred way. Or alternatively, what you can do is you can actually chat with me using the group chat. So that being said, we have like different ways to do the communication. The more we communicate with each other, the better we're going to be able to understand our lecture and then understand the concepts. So don't be shy. I won't be like, judging anyone, right? This is like a learning process. As long as you get involved, let your voice be heard, so you will be able to have more improvement. All right, just kind of like a quick like warm-up words before we get started. All right, if all good, so let's go to our today's lecture. In our today's lecture, we're going to be talking about, this is actually our session 1 sequence and proving strategies in discrete math. Okay. So, I think most of the students, they're familiar with the sequence, right? Sequence is actually a very important concept. You like to know whenever you want to go to AMC 10 or some Canadian math competition, so on and so forth. So that being said, having a good understanding for the sequence-related properties would be very helpful. So in a sequence, we have like two very famous twin brothers, the arithmetic and the geometric, right? Pretty much everyone knows that. And then we're going to be using that kind of arithmetic and geometric as a foundation. We try to introduce more flowery and interesting properties that you can elaborate from the arithmetic and geometric. Well, the most important thing is that for our lecture, we like to teach you guys the conditional react, because there are so many mathematical thought, or there are so many strategies that are not like so complicated or like so flowery. You can remember it. So the problem is that most of the students, whenever they go to the North American math competition, they complain, I can do the problem, but I just don't have enough time. One of the big problem, or kind of like the reason behind that, is you might have to search all the problems, search for all the solutions from scratch. If every single problem you want to think from scratch, doing all those kind of analysis, so on and so forth, it's going to take forever for you to solve the problem. So definitely you do not have enough time in order to solve the problem. However, and the reality is that in the real problems, there are so many action words. Okay? As long as you see this action words, you need to kind of find out a conditional react. Okay? So in the lecture, we're going to be teaching you guys how to build up all those conditional react. As long as you see such a condition, you're going to be automatically doing such a job. You see this, you see that. This is going to be a more like very mechanical process. As long as you have all those mechanical process built up together, so as long as you see new problems, you're going to be doing this in a more, what should I say, intuitive way. You do not have to think from scratch. Well, alternatively, you can just directly, do this and then see this and then do this. This is going to be a very mechanical process. That's going to be really helping you to expedite your solution process, right? This is actually one thing. Well, the other thing which is a focus for our lecture is that we like to teach you guys the thinking process. You know what? there are like so many problems out there. If I give you like 1,000 problem, you might be able to see the 1,001 problem, right? So it is impossible for us to cover all those problems in a limited lecture. However, on the contrary, I like to teach you guys the thinking process. As long as you see such a problem, what do you think? How you can solve the problem? I'm not like reading the answers to you because I have the solution manual. On the contrary, I like you guys to think with me all together, try to analyze all those keywords which is given by the problem, try to use our conditional react to list out all those possible solutions and guiding us using the thinking process, try to eventually solve the problem. So this is basically, the fish and fishing process. I'd like to give you guys a little bit overview. What is the focus of our lecture? What are the strategies we're going to be sharing with you guys? All right. Okay, so before we jump to the details for today's lecture, let's have a quick overview what would be covered in our current session. So this is like a syllabus for our current session. So some of them would be covered in details, some of them will not be covered in too much because we have like two different classes, like higher level and lower level. For the lower level, for something which is not so important for you guys, I'm not going to elaborate too much. In our lecture, we're going to cover something about a mathematical induction method. This is actually a very important method, help you guys to solve whatever properties which are related for like the positive integers. As long as you have a property which hold for certain positive integers, you would be able to use the mathematical induction method help you to solve the problem. So we're going to spend a very quick time talking about the minimum principle and proof by infinite descent. So this is kind of a very flowery way how to solve a problem. And then, because the lecture focuses on the sequence, we're going to spend the majority of our time talking about the basic property and the solution strategies for sequence-related problems. We're going to talk about the general formula of a sequence, which is kind of like a very important property for a sequence. We're going to talk about the recurrence formula. You see, these two formulas are considered to be a twin brother. They're kind of like two formulas try to represent, the properties, different terms within the sequence. And then we're going to try to determine the sum of a sequence. So, sometimes the question gives you a weird sequence with a weird, either it's a recurrence formula or it's a general formula, and the question asks you to determine the first n-term sum, right? We're going to talk about different strategies. However, as long as you see something complicated or something flowery, you can use all the technologies we introduced, try to kind of do some quick analysis. No matter how difficult the problem is, you'll be able to determine the first n-term sum. And of course, we're going to be talking about these two very important sequences, arithmetic and geometric. They are considered to be the prototype. Whenever you go to the AMC or go to the Euclid or go to some other Canadian math competitions, you would be able to see there are so many problems that are elaborated from either the arithmetic and geometric. Having a good understanding for these two basic prototypes is going to be very helpful for us to determine some flowery and complicated sequence-related problems. And if we have some time, we're going to talk something about a high-order arithmetic sequence. And we might talk about some kind of flowery, sequence-related methodologies. One is the eigenvalue and the eigenvector theorem. The other one is a fixed point method. So these are considered to be a very flowery method, help you guys to determine some fancy sequence, either the general formula or the recurrence formula or even the first n-term sum. And then last but not least, we're going to be talking about the Fibonacci sequence. I think pretty much everyone heard about the Fibonacci sequence. And you know what? Most of the time, you only just know such a concept. The Fibonacci sequence is kind of every single term is the value of the previous two-term sum, right? However, Fibonacci sequence has a lot of very interesting applications. You can even use the Fibonacci sequence to find a lot of instances in our real life. So we're going to be using pretty much like one lecture talking about some flowery properties of the Fibonacci sequence, and most importantly, how to use the property from the Fibonacci sequence to try to solve some real problems in the North American math competition. All right, so this is kind of like a quick overview what will be covered in our lecture. We have some unprecise and something important, and something not so important, we just give less time, so on and so forth. And also during the entire lecture, I'm going to be asking you guys from time to time, how do you think the complexity of our lecture? If you think the lecture is too easy or too difficult, always let me know, because we have like a relatively smaller class, right? So I would be able to adjust the complexity of the lecture based on your feedbacks. Okay, if you think it's too easy, I'm going to make it more complicated, or vice versa. So that being said, having more interactions with me, try to participate as much as possible. This is going to be extremely important. So your voice will be heard very loudly, and I'll be able to basically do the adjustment based on your feedback. All right, this is kind of like a quick overview, a syllabus, what will be covered, so on and so forth. If everything is good, let's jump to our first lecture, lecture number 1. We're going to talk about the basic properties of a sequence. Okay, because we're going to talk about the sequences, right? So instead of directly jump to the arithmetic or geometric, let's try to talk about some basic properties of a sequence. So in this lecture, we're not specifying into one type or two types of sequences, any kind of sequences. We might be giving you different kinds of sequences, but let's try to talk about some generic properties of all those sequences. Okay, so the first one, before we jump to all those kind of properties, let's have a quick definition. What is a sequence, right? We know, like everyone knows what a sequence looks like, but what is like the real definition of a sequence? A sequence, we always use the word AN, right? AN with a curved bracket to denote it. So what is a sequence? A sequence is numbers in a certain order. That's it. See the definition, like one-liner, so easy. Numbers in a certain order, that's going to define a sequence. So as long as you see this definition, of course, you're going to see maybe a certain order. That's kind of like the most important thing, right? The most fruitful word in this kind of definition. So what does the order mean? Does the order needs have a specific kind of like enrichment or specific meaning, so on and so forth? Actually, from a sequence perspective, this order, the word order, can be from something very strict to something very loose. For instance, whenever we talk about this order, it could be a very strict order, a very strict order. So what do you mean by strict order? It means the order needs to be exactly followed by every single term. For instance, our famous arithmetic sequence, right? So what is an arithmetic sequence? Arithmetic sequence says any term an minus 1 must be equal to d, right? The distance between any adjacent terms must be a constant value, which is a d, right? So that being said, you have 1, 2, 3, 4, 5, every single two terms. As long as they're adjacent, the difference must be exactly equal to 1, which is quite understandable, right? This is a very strict order. As long as you're not following this order 100%, this is not considered to be arithmetic sequence. Well, on the other hand, the sequence does not need to have every single term follow a very strict order. The order can be very loose as well. So let's say if I define a sequence which is an increasing sequence or decreasing sequence, it means what? As long as an is greater than an minus 1, so this is actually an increasing sequence, right? The terms are getting bigger and bigger. And vice versa, an is lesser than an minus 1. So the sequence value getting lesser and lesser. You see, this one is actually very loose, right? As long as an is greater than an minus 1, an can take whatever value you like to take. It's not like the arithmetic sequence has to be exactly the pattern, right? So this is something you can see the difference, a very strict order and a very loose order. Or you can have no order. No order is also considered to be an order. What is that? I have a random number sequence. Right? It is quite possible you have a random number sequence. Every single item in this item in the sequence is actually a random number. So that being said, there's no pattern, right? So no pattern can also be considered as a pattern, aka this pattern has no rules, no orders. Or even you have some same elements. The same elements in the sequence, they can also be good. For instance, I have a constant sequence. 1, 1, 1, right? The sequence has no values except 1. So this is like a constant sequence. You see, all the way come to here, we just not have a good understanding. Whenever you see the sequence definition, it's actually very loose. Can be very strict order, a very strict pattern, all the way to, almost like no pattern. You can do whatever you like. So that being said, the way to construct the sequence is actually something very basic. You do not have to have a lot of black and white rules. As long as you follow one of them, you'll be able to generate a sequence. This is something quite understandable, right? So the second part is, sequence, we always use the definition or the denotation, AN with a curved bracket, right? Everyone knows that. And also, think about it, in our entire math, there's another very important concept. We also use the same thing. A number using a curved bracket. Do you know what kind of definition, what kind of mathematical concepts also use something like this? Can you think of that? AN, BN, or even CN, whatever, right? We can use something similar, some numbers together, and then I make a curved bracket. You guys can think about it? This is also a very important concept. You pretty much learn that from day one.
I am thinking about it.
Think about it. Yeah, I'll give you some time. Think about it. What kind of very important concepts? I can give you a quick hint. This concept is the foundation of our function. The foundation of our function. How do you get a function's definition? Do you guys know this?
No.
Yeah, no problem. I'm going to give you guys the answer. That's the set. Can you think of that? Set. What's the definition for set? What is the definition for function? The function is actually a mapping from one set to the other set, right? That's our mapping. We talked about it in our function session, right? But generally speaking, set is actually a very important concept. It's kind of considered to be a foundation concept, right? And you know what? Function and like the set and sequence, they're using a similar denotation. Something, and then you make a curved bracket. But as long as you're talking about two different things, but using the same denotation, let's try to do a quick comparison between the two to see how you can differentiate these two concepts as long as you're looking at the similar denotation. Okay, so this is more like a difference between one is the sequence, the other one is the set. I think generally speaking, there are two major differences between the sequence and the set. The first one is in the sequence, order of your elements matters. Let's say I have a sequence 1, 2, 3, 4, all the way to 5. For instance, this is my first sequence, and my second sequence is 5, 4, 3, 2, 1. So these two sequences are having exactly the same item, right? However, one is increasing order, the other one is decreasing order, right? So that being said, there are two different sequences, right? Because according to our definition, one is actually increasing order, one is actually decreasing order. Of course, you have two different sequences. right? If you want to think about it from the arithmetic way, the first sequence, the arithmetic's common difference is equal to 1, while the second one is equals to -1, right? This is like the basic definition for that. However, if the same thing goes to set, the order of elements in the set does not matter, right? So you have a set 1, 2, 3, 4, 5, or you have a set 5, 4, 3, 2, 1. These two sets, they're exactly the same thing, right? Set doesn't really care. Set is more like a collection of items. As long as you have 1 to 5, all those 5 items, I don't really care who goes first, who goes second, so on and so forth. They are considered to be the same set, right? So this is the basic definition from a set perspective. Well, this is actually the first difference between the two concepts. Well, the second part is, can you have the duplicated items? Of course, in the sequence, you can have duplicated items, right? Because we have like the constant value sequence, but not to say duplicate. Every single item in a sequence have exactly the same value, which is quite understandable, right? However, from a set perspective, is duplicated items allowed or not? Do you guys notice? In
It's
the
not
set,
allowed.
right?
Yeah.
That's perfect. In set, you can't have duplicated items. There must be unique item. I don't really care the order of this item, but all of the item must be unique, right? So 1, 1, this is not even a set. So that being said, these are the two major differences between a sequence and a set. As long as you have these two major differences, so it will be very rare that you can mess up with these two. So that being said, in any kind of problems, as long as you see sequence, you see set, you would be able to see, you know what, there are definitely two different concepts. You won't be able to mess up these two concepts. Okay, so I think these are something quite understandable just as a quick warm up. Okay, how the sequence looks like, what is the basic definition, so on and so forth. All right, as long as we're done for this, let's go to a very important topic for today's lecture. What are the basic properties? Basic properties of a sequence. Right? Let's try to see what are the basic properties. What are the basic ways for us to evaluate and basically to present a sequence, so on and so forth. Well, the first part, whenever I talk about a sequence, the first part we want to talk about is the general formula. What is a general formula? You know, sequence we can actually write into 1, 2, 3, all the way to whatever n, right? Okay. So if we do a comparison between the sequence and the number, right? Sequence is actually, see, it's actually different numbers mapped on the first, like the first item, the second item, the fourth item, so on and so forth, right? All the way to the nth item. So you're considered to be that you have a function which is defined in the natural number, right? So function, we're going to see something like this. Let's say I have a function which is fx, right? So normally speaking, there's a domain for fx. X can belong to R, can belong to whatever, right? However, what about a sequence? Sequence, you can also take it as a function, but this time the domain is no longer all the real numbers, and must be positive integers, right? So a domain of a sequence function is more like considered to be all the positive integers rather than all the real numbers. So that means that sequence can be considered as a function. Well, the only difference is the sequence function's domain is only positive integers. So that being said, as long as we're all on this same page, we will be able to say a sequence value can also be defined as a function's representation, right? So an is actually the value of the nth term in the sequence, And how to determine the nth term of a sequence, you can basically find out a function, find a formula for us to do this calculation, right? So that being said, as long as you can find out a formula or expression for you guys to determine the for you guys to determine the item in the sequence right away, so these kind of function or formula we give a name. This is the general formula. So long story short, general formula is a formula that helps you to determine the value of a certain term in the sequence. As long as you know the general formula, then you will be able to determine every single items in the sequence, right? So general formula is actually a function between a sequence value and also the term number. Term number means it's the first term, the second term, all the way to the nth term, right? I think this is something quite understandable. So I have to say that general formula is the most powerful way for you to determine the sequence, because as long as you know the general formula of a sequence, then you will be able to determine every single item in a sequence. You don't really have to do any kind of calculation. You can jump to any single item. This is quite understandable, right? So for instance, what is the general formula? For instance, this guy, an equals to n, right? This is our general formula. Okay, as long as you understand the general formula, it is very important. Let's go to the recurrence formula. So what is a recurrence formula? Well, if we do a comparison, general formula focuses the sequence value and the term number. As long as you give me a term, I'm going to be able to generate a sequence value for that specific term, so on and so forth. Well, sometimes in some sequence, it is very difficult for you to determine what is a general formula. However, alternatively, I can find out the relationship between certain adjacent terms. Give you an example. In some sequence, let's say an equals to an minus 1 plus an plus 1. Okay, so that being said, for this specific sequence, you would be able to find, okay, I don't really know the general formula. I don't know if you ask me, hey, Alex, what is the value for this 100 terms? I don't know, but I always know that any single term is actually the sum between these two neighbors, right? If 1, 2, 3, let's say, if this is 1, this is 2, so the next one is going to be 1, right? Because these two terms, adding them together, go to this guy. And then this guy, these two terms, adding them together, go to this, is going to be minus 1, right? And then moving forward, the next one is going to be maybe minus 2, so on and so forth, right? So that being said, in this specific sequence, you won't be able to determine the value of a sequence right away. Let's say, what's the value for a 1000? You might not be able to do the definition right away. However, you can always find out the relationship between, certain adjacent terms or even more terms. I'll give you an example. This is like the 1, right? The number is always the sum between these two neighbors. Or you can do something more complicated. Maybe an minus 1 times an minus 2, and then 1 plus an minus 3, an plus 1. Something like, you can have like a more flowery, more complicated relationship, right? But as long as you're talking about the relationship between several adjacent terms, so this kind of representation, we give a name. This is the recurrence formula. So why you have the name recurrence means the value is not defined right away. You have to be recursively, step by step, in order to define all the values of a sequence, right? This is the recurrence formula. So as these two very important definitions of a sequence, recurrence formula or like a general formula, you can always try to find out some relationship between these two formulas. So actually, in our lecture, we're going to spend a lot of time talking about how can I calculate the general formula using the recurrence formula. As long as I give you a sequence, I give you a very weird, complicated recurrence formula. How can I take it from there and calculate the general formula of a sequence? Why? This is very important because the general formula, as long as I got it, I can directly jump to A1000. I can jump to A10,000. However, the recurrence formula, you have to do it step by step, right? Sometimes if we can use the recurrence to determine the general formula, we will be able to expedite the calculation process significantly. Okay, that's the general formula and the recurrence formula. So here, a very quick and a very understandable part is that for many, many sequences, the general formula and the recurrence formula, they can be calculated at the same time. So you can say, for some sequence, an equals to an minus 1 plus d, right? This is a what? This is actually a arithmetic sequence. So this is actually the recurrence formula, right? And the general formula can be this, right? So sequence have a general formula, sequence has a recurrence formula. You could basically find out, okay, what's the relationship between the two? Okay. And moving forward, number 3, there are some sequences. You know what? You can't even find out a general formula or recurrence formula. You can just only use your language to use some description to describe the sequence. I give you a very interesting sequence. The sequence goes like this. As long as n, give me one thing. So let's get started with a function, right? There is a certain type of function, okay? As long as when x belongs to a rational number, the function value goes to 1. As long as the value goes to irrational number, the function value goes to 0. You see, there are some functions, right? It is kind of very difficult for you to find out how to present it. You know, this is very understandable using human language, right? So x can be all the real numbers. As long as the x value is irrational, the function's value is 1. As long as the x value is irrational, the function value is going to go to 0. So if I really draw out the graph of this function, because there are infinitely many rational numbers and infinitely many irrational numbers, so my function's value is more like this, right? There's so many guys equals to 0. There's so many guys equals to 1, right? And also you can find out in our algebra, we can actually prove any rational numbers. Between any rational numbers, there is at least one irrational number. And also between any irrational number, any two irrational numbers, there is at least one rational number. So that being said, you have like so many values, right? So they're like the dot here, here, all the time. So that being said, you have a function. So this function, there's no way for you to use any recurrence or any general formula to represent it, right? So this is like a function. You can also define something similar from a sequence perspective. It is quite possible you have some sequences. There's no way for you to find out a general formula or recurrence formula. You can only use this kind of description method. This is more like using a human language, try to describe how this function or how this sequence looks like, right? So this specific, especially for this specific example, we call it, this is the Dirichlet function, Dirichlet, okay? Dirichlet function. And we can actually define a Dirichlet sequence based on this Dirichlet function. But good part is for our high school math, most of the time, there's no, so you don't have to worry about this too much. So most of the sequences that we will see in our math competitions, they're either using a general math, like a general formula to do the definition, or you can use the recurrence formula to do the definition, or even you can use both to do the definition. So this is something you do not have to worry about too much. Okay? So if all good, let's continue. As long as we know the general formula, as long as we know the recurrence formula, the next step, extremely important thing is, from time to time, the question always asks you to determine the first n-term sum of a sequence. Okay, the first n-term sum of a sequence. Let's say I have a sequence A1, A2, all the way to AN, right? So the question asks, okay, what's the value for S10? S10 means the first 10-term sum. Okay, what's the value for Sn? The first n-term sum. So that being said, we would be able to determine a sequence first n-term sum using the basic property of a sequence. What are the basic property? We just mentioned two, right? Either we're using the recurrence formula, or we can use the general formula. So in the real problem is that you always, from time to time, you're going to be able to see the question give you a sequence. The sequence you can determine either the recurrence formula or the general formula. And taken from there, you want to use the either general formula or the recurrence formula, help you guys to basically determine the first n-term sum. Okay, so this is more like from the general formula or the recurrence formula. Okay, so all the way comes to here, maybe you have already realized, okay, looks like the general formula and the recurrence formula, they are the foundation of the sequence. Having a good understanding for these two important formulas and elaborate it from there, you will be able to do a lot of interesting stuff, right? So for our high school math competition territory, generally speaking, understanding the general formula, the recurrence formula, and also the first n-term sum will be extremely important. And we will be able to see many, many problems are basically created based on testing you these three very important concepts. Okay, I think these are something quite understandable. Our lecture number 1 is always easy. It's kind of like introductory. So let's continue the next part. As long as we understand all those basic concepts, there are some extra concepts you need to know. Some extra concepts you need to know regarding a sequence. The first one we're going to talk about is the finite sequence and infinite sequence. Infinite sequence. What is that? So finite sequence and infinite sequence means basically like the term, right? If all the terms of a sequence is limited. So let's say the sequence you have like 1 trillion term, right? 1 billion term, 1 trillion term. It doesn't matter. 1 trillion is big, but considered to be infinitely many, 1 trillion is still like a finite number, right? So finite sequence means all the terms of the sequence is actually a number you can count. While infinite sequence is actually a number is all the term of the sequence is unlimited. For instance, our general, let's say, give an example, the natural number sequence, all the natural number sequence will be an infinite sequence, right? Because there are infinitely many natural numbers, which is quite understandable. Okay, so finite, infinite is pretty much talking about the terms, how many terms in a sequence. The second part is we talk about the increasing sequence, decreasing sequence. So what is a increasing sequence? So everyone knows that, right? The number is getting bigger and bigger. So how can I use a mathematical language to present the numbers getting bigger and bigger? Let's try to use a short and brief formula expression to see all those kind of like English languages. We can see for any given n belongs to positive integer, an plus 1 is greater than an. So here people will say, what does that mean? This is actually a mass denotation. It's a mass symbol. This symbol is kind of like an A, right? We make it upside down. This one means for any given. You kind of like make a long word, right? A long phrase into one little symbol. So A upside down means for any given. Or you know what? Why they have this? You can take it as arbitrary, like the word arbitrary. For any given means arbitrary. Right? For any given n, you can always make sure an plus 1 is greater than an. So that being said, this is going to be an increasing sequence. Quite understandable, right? And what about a decreasing sequence? For any given n belongs to positive integer, an plus 1 is lesser than an, right? Exactly the same thing. We just basically make it reversely. Quite understandable, right? Okay. Number 3, another very important sequence we want to say, we call it a bounded sequence. What is the bounded sequence? Bounded sequence means the value of the sequence has a cap. Okay, a student got a question, what does n star mean? Okay, n star means natural number. One, two, three, up to whatever. This is the definition for natural number. Okay, because in math, there's a lot of ways for you to denote something, right? So this is like a way how to present, how to denote all the natural numbers. Okay, let's go back to here. What is a bounded sequence? A bounded sequence means the value of a sequence. Okay, there's a boundary, there's a cap. The value can't be too big or the value can't be too small. So these are considered to be a bounded sequence. But how to say that, you know, can't be too big, can't be too small? This is kind of like a human language. How can I use a mathematical language to try to represent it, right? There's another mathematical way to try to represent it. For any given n belongs to n star, which is the natural number, there exists, okay, this is another symbol I wanted to tell you, means there exists. So it basically comes from the word exist, right? And then this time, because E, if I take upside down, it's the same thing. So, right, E, I take it upside down, it's still E, right? So this time I'm going to take a flip, left to right. So you'll be able to see this is, okay, this is like a denotation I created from an English word. There exists a number n such that an's absolute value is less or equal to n. Then an is called bounded sequence. Okay, what does it mean? It means that for any given n, 1, 2, 3, 4, up to 1 trillion, like whatever, there always exists a number m such that all those kind of an is lesser or equal to n. It means that you can take whatever value, your a1, a2, 1 billion, 1 trillion, 1, like whatever, regardless, whatever number you want to choose. I can always find a number. This number is always greater than your sequence. So that being said, your sequence is actually bounded. Okay? So this bounded sequence actually has two definitions. You have a upper boundary. You have a lower boundary, right? So your value can be up and down, up and down. When I can, okay, I don't really care. But regardless how you're going to do the up and down, you can never ever go outside my boundary. Okay. So how are the sequence? What kind of sequence goes like that? Give an example. Let's say sequence equals to 1 over n. Okay, I have a sequence. The general formula is 1 over n. So how does sequence look like? 1, 1 over 2, 1 over 3, all the way to 1 over n, right? So this sequence, if I write out all the numbers, 1 over 2, 3, it's getting closer, closer, closer. But you know that, right? It can never touch 0, right? This is going to be the asymptote for this, right? So, and 1, yeah, 1 is like the first time. As long as n equals to 1, you'll be able to touch the value 1. But as long as you're no longer n equals to 1, all the other values, you want to make sure the an is actually lesser than 1. So that being said, you have such a sequence. This sequence, the upper cap is 1 because you never go up to 1. And the lower sequence is 0. It's going to be very close to 0, but you will never ever touch 0. So this is actually a very standard, a very typical representation of bounded sequence. Is that right? Or I have some other sequence, for instance, an can be minus 1 to the power of n, 1 over 1. 1 over 1, okay? In that case, my sequence value can be positive, negative, up and down, right? So the first time is actually here, minus 1. And then I go to positive 1 over 2. And then negative 1 over 3, positive 1 over 4, so on and so forth, right? Again, getting closer to the x-axis, very close, but you never ever touch it. So that being said, this sequence actually has two boundaries. One is minus 1, you touch it whenever n equals to 1, and also 1 over 2, as long as n equals to 2. As long as you are more than these two guys, like more than 2, the expression of this sequence is always going to be between minus 1 and 1 over 2, which is quite understandable, right? Okay, quite understandable. Or another very good example, let's say an equals to sine n, right? You guys know this basic sinusoid thing? Let's have a quick survey, okay? I know it's our old students for sure, but for our new students, are we familiar? So do you guys know this basic trigonometry thing?
No.
No? Okay, yeah, so we have some students who are kind of new. So this is like a trigonometry. So it's kind of like a way how to define the angle relationship between a triangle, so on and so forth. So basically, I'm not gonna expand it too much. Basically, this function goes like this. As long as n is actually taking all the values from here, then you'll be able to see the value of the sine n is always between positive 1 and negative 1. Just long story short, this is also another way try to present the sequence, make sure they're actually fluctuating between two values. Okay, so these are something quite understandable, quite basic, right? So these are like the basic concepts of a sequence. Like I said, for our first lecture, we're not going to go to the arithmetic, geometric, something like that. Let's try to see some generic sequence and how to find out the value, how to determine all those kind of properties of this generic sequence. Okay, so before we jump to our questions, so generally speaking, in the sequence section, the question might asking you two major problems. Typical questions. What are the sequences related problems you might be expecting in your North American math competition? The first one is determine the value of a certain term. Okay, the question might give you a sequence and then ask you to determine the value of a certain term. So here, let me try to teach you the common strategy how to solve a problem. So as long as you see such a problem, you're going to be asking for yourself, if the question asking a small value, a small term value, let's say ask you to say, what is value for A10? What's the value for A8? Most of the time, you can directly do the calculation. Nothing too flowery, right? You can just do the calculation, figure out what's the value for it. However, if the question asks you to determine a big term value, let's say A2019, A4008, something like that, then 100%, that you won't be able to do the calculation right away. You have to solve the problem in a smart way. Okay, so generally speaking, as long as the question asks you to determine a relatively larger term, there are basically two major solutions. One is there must be a pattern for the value. What is that? So that means that so the value of a certain term and the term value itself, like 2009, let's say the value of this 2009's term, which is A 2009, and also the term value 2009, there must be a very simple relationship between it. Okay? So that being said, as long as you want to find out the relation, as long as you can find out the relationship, you'll be able to solve the problem right away, right? But how can you find out the relationship? So the most important way is just try to list out the first couple of terms, doing some enumeration. Okay? So the question might give you a lot of weird conditions, so on and so forth. Don't be panicked. You just have to list out the first couple of terms. And taking from there, the question will speak for itself. You will find out a pattern and use the pattern without a very deep, rigorous proof. You'll be able to determine a very large terms value. Later, I'm going to give you some examples, and then you'll be able to see how you can find out such a pattern, how you can use this pattern to try to solve the problem. Okay, this is like one typical way whenever you see such a problem. There must be a pattern, find out a pattern, do some enumeration, list out the first couple of terms, and then you'll be able to find out the answer right away. Or alternatively, you won't be able to find out a very strict pattern for the solution. However, you'll be able to find this is a periodic sequence. So what is a periodic sequence? It means maybe 1, 2, 3, for instance, right? The term starts with 1, 2, 3, and then go to 1, 2, 3, 1, and then go to 1, 2, 3, one more time, so on and so forth. Just like a periodic function, the sequence repeats itself after a certain number of terms, right? Let's say if you find out this pattern, which is a sequence, you have a sequence, period equals to 3, and then the question asks you to determine what's the value for A 2019, then you will be able to solve it fairly quick. Right? A 2019, you just basically find out, okay, what is the corresponding value for A 2019? And taking from there, you'll be able to get a problem solved. Right? Find out A 2019 maybe basically equals to A2 or equals to A1 or equals to A3. Find out the correspondence for this specific iteration, and you'll be able to get what you need. Right? So bear in mind, these are two very important strategies. As long as the question asks you to determine a relatively larger term in a sequence, and you can basically solve the problem using that. Okay? Later, I'm going to show you more examples how you can use this solution, try to solve either a pattern problem or periodic problem. So this is actually the first problem. The question asks you to determine the value of a certain term. So this one actually takes 90% of the sequence-related problems. So you can see this one is actually very important. The other part is basically ask you to determine the sum. First n-term sum of such a sequence. Okay, so for the first n-term sum, it can basically ask you for two ways. One is actually easy. Let's say you can go, let's say, as sum as 100. Let's say you just try to find out the first, basically first 100 terms, right? Adding them together, give me the value. That's a very direct way. And sometimes the question can be a little bit, this is actually number one. Number two, the questions might be a little bit indirect. Let's say the question asks you to determine A1 all the way go to A100. This is also first 100-term sum, right? But there's no way for you to figure out how to add all those 100 terms together. Then you might have to do some splitting method. splitting this entire 100 terms maybe into, I just give an example, A1 plus A2 all the way to A5. This is actually one term. A6, A7, A10, second term. A11, A12, A15, third one, so on and so forth. All the way you go to the last one is A100, right? As long as you break it into small groups, you might be able to find out maybe this is your first solution, that's your second solution, third solution, so on and so forth. You might, what should I say, happily find out that this guy might create another sequence. There might be an arithmetic sequence, there might be a geometric sequence, there might be some other fancy sequences. So that being said, if you can't directly do this 100-term calculation, no problem. Try to do some grouping. Grouping them, splitting them into small groups, and then grouping them into small groups, you might be able to find out a pattern for these small groups rather than like a big overall pattern. Okay? If you find an overall pattern right away, directly use method number 1. If this entire sequence is an arithmetic sequence, just use the arithmetic sequence calculation, right? How to do this calculation right away. But sometimes, the questions are not so nice. They give you some problems. There are some patterns, but this is not an overall, this is not a global pattern. In that case, try to break it into small pieces, small groups, and then hopefully you'll be able to find out a pattern between these little small groups. This is only a big direction, right? We're going to be giving you guys like more real problems that you can see the rationale behind it. But this is kind of like a thinking process. As long as you can solve the problem in one shot, let's try to break it into small pieces. Hopefully there are some patterns for all those little small pieces, and you'll be able to solve the problem fairly quick. All right? So far, so good? Perfect. If all good, I think that's pretty much what I want to say for our pretty much like entire lecture number 1, talking about the concepts, because the concepts are fairly easy. This is only lecture number 1. Now let's try to see some real problems. We're going to give you some problems from the Canadian, from the American problems, all over the places, blend them together, right? Let's try to solve some real problems using all the strategies we introduced in today's lecture. Okay, so our second part will be problems. Okay, we're going to use some easy problems, some relatively difficult problems. Let's try to see how we're going to solve the problems from different real math competition course. Let's go to our lecture number 1. Let's go for an easy problem first. So we're looking at a problem that comes from 2008 AMC 10B. Question number 11. It's a fairly easy problem. So I'll give you 30 seconds, read the problem first, and then let's try to do some discussion all together. All right, so let's have a quick look at it. Suppose UN is a sequence of real numbers satisfying. You see, this is actually what? This is a recurrence formula, right? Recurrence formula denotes the relationship between any adjacent terms. UN plus 2 equals to 2 UN plus 1 and UN. Okay? And that U3 equals to 9, U6 equals to 128. With all those information, try to find out the value for U5. Okay, how to deal with such a problem? Think about it. How can I deal with such a problem? The question gives you a recurrence formula, which denotes the relationship between different terms, whatever, right? And then the question gives you 2 terms, U3 U6. With all those information, the question asks you to determine U5. How can I determine U5? Who can tell me? Please try to participate in our discussion. It is extremely important, right? Let's go for the discussion altogether. How can I figure out, how can I determine the value for U5?
By U3 and U4.
Can you say that one more time?
By U3 and U4.
Is that right? I think that's a brilliant observation. Because I need to determine U5, I need to have U5 presented, right? If there's no new U5, how can I determine U5, right? And how can I get U5 involved? Of course, that's pretty much the only condition, right? This condition reveals the relationship between any adjacent 2 terms, 3 terms, whatever. And then I need to create U5 from such an expression. Okay? So, just like Stephen mentioned, the most powerful way is just try to find out the value, right? We can let n equals to 3, right? If n equals to 3, you have U5 equals to 2, U4 plus 9, which is our U3, right? I'm just going to put it here. And then we can let n equals to 4, then you have U6, which is 128 equals to 2, U5 plus U4. So easy, right? Easy peasy problem. You just got to answer right away, right? Well, the thinking process is for such a problem, if the question asks you to determine U5, you must create, or we use a more professional word, you must construct. Doing a construction, you must construct U5. If there's no U5, how come you can create an answer? But how can you construct the U5? You just have to go to the recurrence formula, from the recurrence formula, find out the relationship, and taking from there, you'll be able to determine all your U4 and U5. Right? This is something quite understandable. You need to create something whenever something is not there in the first place. Okay, in that case, who can tell me what's the value for this? What's the value for U4 and U5? Having some calculations is very important. As long as we have some easy problems, I want you guys to get your hands dirty and tell me what's the answer for this calculation. Please, everyone, please participate. In our bootcamp lectures, we're like super tight. We don't even have any time to talk about it. But for now, it's actually fairly loose, right? So we want to make sure everyone can participate in the process.
I think it's 53.
Is that right? You guys have the same answer?
I think so too.
Perfect, right? That's a very easy calculation. U5 equals to 53 and U4 equals to 22, right? Something quite understandable. This is like an easy peasy problem. Okay, if all good, let's go to our second problem. Our second problem is a problem that comes from Euclid. Number 2. There you go. So this is a problem that comes from 2018 Euclid, question number 4. Euclid is for grade 12, right? But you know what? Like the relatively easy problems, we can, even though for grade 9, we can basically take care of it. So let's try to pick up some relatively easy Euclid problem, try to feel this thinking process, the strategies, how to solve a problem. Okay. Let's have a quick look at this problem. A function f is defined so that f1 equals to 1, okay? If n is an even positive integer, fn equals to fn over 2, because it's even, so n over 2 will be an integer, okay? And if n is an odd positive integer with n greater than 1, fn equals to fn minus 1 plus 1. Okay, so that being said, your function fx, or fn is actually defined in two different ways. As long as the n is even, you go for one strategy, one way on the top. As long as n is odd, you can basically go to the second one, right? So basically, the function is defined by even and odd. For example, the question give you an example. So f34, because 34 is an even number, so f34 equals to n over 2, which is f17, right? And what about f17? f17 is an odd number. f17 needs to be defined by using fn minus 1, which is 16 plus 1. That's something quite understandable, right? With all those information, the question asks you to determine what's the value for f50. For f50. Well, a problem like this, 50 is not too big, right? This is not 50,000, but 50 is not very small. Very small as well. So maybe we have to follow the rules, follow the pattern given by the problem, and try to calculate the value for this, right? So in this problem, you're going to see in sequence from time to time, a very important thing is you need to follow the pattern. Right? You need to follow the pattern. So not to say 50 is too big or too small. Who can tell me what's the value for 50 according to our definition?
25. F25.
Is that right? So easy. Fn equals to Fn over 2 as long as n is an even number. And what's the value for F25?
25. F24 plus 1.
Is that right? Because whenever you see 25, no, 25, F25 does not equal to 25. F25, because 25 is the odd number, you need to basically go for such a way. 24 plus 1. Okay. Now I see 24 one more time. So what's the value for 24?
F12.
Is that right? But don't forget, plus 1 is always here. And then what's next?
F6 plus 1.
Is it right? This is quite understandable, right? You just basically follow whatever pattern the question asks you to do. And what's the value for F6?
F3 plus 1.
3 plus 1, right? And then F3 means what?
F2 plus 1.
So easy, right? And then what's the value for F2?
F1 plus 1.
Is it right? And what about F1? The question already give you for F1. You see, so easy. F1 equals to 1. So the value goes to 3. So that being said, as long as you're dealing with the sequence-related problem, you just have to follow the pattern, right? If the question gives you the pattern, just follow the pattern. Sometimes the question does not even give you the pattern. You have to figure out the pattern by yourselves, right? Because if you remember what we mentioned, finding out a pattern by using some enumeration, by listing out the first couple of terms, there's a totally a very important strategy you have to remember. But this problem is so easy. The question already gives you the pattern. You don't even have to think about too much. You can have the value right away. So far, so good. I think this is something quite understandable. Okay. So if all good, let's go for another problem. See, all the sequence problem, especially our lecture number 1, they're considered to be easy problems. As long as you follow the pattern, you will be able to get a problem solved fairly quick. So now let's look at a problem that comes from 1998. It's a very old problem. Euclid, question number 4. So this time, I will give you 2 minutes. Try to think about this problem and try to see how you can solve the problem. Later, I'm going to ask some students, if you have your correct answer, put it into the group chat. I'm going to be asking some students to give us some ideas. again, you need to follow the pattern, right? Find out the pattern, follow the pattern, you get what you need. Please, everyone, please participate in this discussion process. Try to get your hands dirty, do some calculation, and then you can let me know what did you find out. Think about it. How can I deal with such a problem? Okay, let's have a quick look at this problem all together. I'm going to give you some hint. Okay, consider a sequence. Okay, this sequence is also t1 equals to 1, t2 equals to minus 1. It's quite similar with our previous question, right? The question give you like two initial terms, whatever. And tn, okay, this time the sequence looks like a little bit nasty. Tn equals to n minus 3 over n minus 1 times tn minus 2. Okay, so it's not adjacent. There's like a one skip, right? Tn minus 1 is skipped. But basically, Tn minus 2 and Tn minus and Tn, there's a relationship. The proportional is n minus 3 over n minus 1. Whenever n is greater or equal to 3. Then what's the value for T1998? As long as this is actually what we mentioned in our previous lecture, right? In our previous part. As long as we're looking at a weird number, 1992, 1998, of course, you won't be able to do the calculation right away, right? You'll have to do some quick analysis and then try to find out a pattern. Taking from there, you'll be able to solve the problem. How can you find out a pattern? Okay. The question asks you to determine what's the value for, T1997, 1998, excuse me. So, the pattern, right? As long as you get a pattern, the work is done. How can I get a pattern? Who can tell me? How can I get a pattern? I'll be asking for.
List it out.
Is that right? Yes, you just list them out, right? So, you know what? Maybe I'm going to be asking some students to give me some other insights. Maybe Stephanie, can you talk? If you can talk, you can basically let us know, what do you think? I just wanted more guys to get involved, more opportunities to speak. Can you talk? Okay, so you can't talk. Okay, no problem. So in that case, let's try to think about it. Let's just, like Stephen mentioned, let's try to list them out. So T1 is equal to 1. I don't really know what it is. T2 minus 1, that's it. T3. T3 is what? 0, right? You just plug in the value. T3 and T1, there's a relationship. Plug in the value. T4 is minus 1 over 3. T5 is 0. T6 is what? Minus 1 over 5. Okay. So all the way comes to here. Did you find out any patterns? Did you
It
find?
just decreases by like the so like the denominator, it just like decreases by 2, and then it just turns into 0, and then goes back to the original one, but it is 2 times.
Okay, that's a very nice observation. So if you find out such a pattern, can you tell me what's the value for T 1998? Are you comforted enough that you already find a pattern for T 1998?
Yeah, like every even number you will have like a actual number, but for every odd number you would have a 0 or 1 at the beginning. So
Okay.
then wouldn't
Yes.
T 1998 be negative 1 over 1997 because it's
Is
1
that
left
right?
the top.
That's a brilliant observation, right? So you just basically see all the odd numbers will go to 0, and all the even numbers you just see, all the even numbers will be minus 1, and then looks like this guy is actually one number higher than this guy. So Tn will be n minus 1, right? Whenever n is equal to odd, n is equal to even. Is that right? So that's the pattern. You don't really have to give a rigorous proof, right? As long as you know the pattern, you're good to go. So that being said, your T 1998 will be minus 1 over 1997. Do we have it? Yes, this is actually a question you can just basically plug in the value. Minus 1 over 1997. You see? Like so easy, right? The only thing you need to do is to find out a pattern. There's no need for you to give a rigorous proof, so on and so forth. How can you find out a pattern? You just list out several terms. As long as you list out several terms, the question will speak for itself. If you're not happy with here, you can actually try to list out more terms, right? T8. As long as you're happy, you're confident enough, you'll be able to find out a pattern and you can solve the problem right away. Okay? I think this is quite understandable problem for this. And also, you know what? This is actually a more finding out a pattern. I can also give you a more direct way how to solve it. So our solution number 2, let's say we already know Tn equals to n minus 3, n minus 1, Tn minus 2, right? If that's the case, the question asks you to determine T 1998. You just plug in a value. T 1998 will be what? 1995, 1997, T 1996. Is that right? This is quite understandable. But what's the value for T 1996? We can use the definition one more time. That guy is going to be equals to, I'm going to write it here, 1995, 1997, and 1996 will be 1993, 1995, T 1994. Is that right? And then you keep writing the second thing. 1994 can be written as what? 1991, 1993, T 1992. Right? You can keep writing that again, and again, all the way to the end. You're going to have 1995, 1997, 1993, 1995, 1991, 1993, all the way 3 to 5, 1 to 3, T2. And you can find out all those terms could be canceled. All those adjacent terms could be canceled, only remaining your first denominator, last numerator. So this is going to be minus 1, 1997. Why? Because T2 equals to minus 1. T2 equals to minus 1. You see? This is another more rigorous way how to solve the problem. But I think you don't really have to waste your time doing this. As long as you list out the first couple of terms to find out a pattern, you're good to go. There's no need for you to do too much rigorous proof, so on and so forth. So far, so good. As long as you know this could be very helpful, help you to determine all those kind of important, terms or values directly by using the pattern. All good. Let's go for another problem, right? We're going to try to give you more interesting problem. You're going to find out the American and the Canadian exams, they're basically the same thing. Using the pattern, solve the problem. So let's go to our question number 4, right? Let's go for an American problem. This time we're going to go to number 2. There you go. Let's go for an American problem. This is a problem. This is also an easy problem from 2005. AMC 10B, question number 11. So the problem says the first term of a sequence is 2005. Okay, I give you A1, 2005. Each succeeding terms is the sum of the cubics of the digits of the previous term. The previous term, every single digit, you want to make a cubic, adding them together, you'll be able to get the second term. It's kind of difficult for me to write out like an expression. This is actually a recurrence formula, right? This is a recurrence. But it's kind of difficult for me to write you like a math expression how this recurrence formula looks like, but you get an idea, right? Every single term of, every single digit of the previous term, make a cubic, adding them together. With all those information, the question asks you, what is the value for the 2005th term? Again, 2005 is actually a big number. You won't be able to really find out the value. The only thing is there must be a pattern inside. So again, I'll let you guys tell me what the pattern looks like, and we can take it from there.
What it mean like by the cubes is like we add
give
the
an
2
example.
and 5 together.
Yeah.
So what does it mean?
Sure.
Like when
Exactly. I'll give you explanation. If this is A1, right, 2005, then what about A2? A2 is determined by the sum of the cubes of the digits of the previous term. So what are the digits of the previous term? 2, 0, 0, 5, right? You want to make the sum of the cubic. 2 cubic, 0 cubic, 0 cubic, 5 cubic. The sum of the cubic of the digits of the previous term. Okay, so that being said, your A2 will be 133. So this is the meaning why you have the sum of the cubic of this. Sum of the cubic of the digits. Give you some time, think about it. How can I deal with such a problem? Think about it. How can I deal with such a problem? I think the most important thing is you need to find out a pattern, right? How this pattern looks like. So like I said, don't be afraid of, don't be panic. There must be a pattern. If you can't find out a pattern in your first 2 terms, 3 terms, just keep writing. As long as you get a pattern, then you'll be good to go. I see somebody already has the correct answer. And what about the other students? Yeah, I see Glenn has the correct answer. So why don't we ask Glenn to give us some ideas? What do you think?
I started listing out the terms and I found out that after the fourth term, it repeats back into 250, which has the same digit cubic sum as 2005 because they both have a 2 and a 5. So there is a repeating pattern there. And of like 3 numbers, so I divided 2005 by 3 and then went from there.
Is it right? That's a brilliant observation. So like I said, don't be panic. If you don't know what a value looks like, it looks like this definition is a little bit weird using the digit cubic of the digit sum, so on and so forth. Let's try to close our eyes, keep writing all the numbers, and then hopefully you'll be able to find out a pattern. So A2 equals to 133. A4, you just plug in the value, right? 1 cube, 3 cube, another 3 cube, 55. A5, 250. You see there's no pattern. 2005, 133, 55, 250. No worries. Just keep writing. And the next one is going to be A6, 133, A7, 55, A8, 250. Hey, look. Check it out. There is a pattern now. See? It looks like after your A5, the sequence looks like it is repetitive, right? Well, the first one, there's no pattern, but starting from the A2, A3, A4, right? And then you will be able to find out, okay, it basically repeats itself. It basically repeats itself. So this is going to be what? A periodic sequence, right? This is going to be a periodic sequence. So like I said, if the question asks you to do something weird, either this is going to be a periodic sequence or there's a very conspicuous pattern. So you don't know which one is right, right? No worries, just list them out. And then you will be able to find out, okay, which one will be the answer. So for this time, the answer is very conspicuous. This is going to be a periodic sequence. The sequence is actually, the period is 3. So that being said, you have to figure out 2005 actually equals to what kind of period in such a thing, right? So if this is a 3 as a period, however, the first one you have to remove. So A 2005 actually equals to A5. And this is something quite easy, right? You find out what is the position for this 2005 in such a big circle, right? This is going to be a period, 3 as a number, 3 as a number, so on and so forth. This is going to be A5. And A5 is actually 2000 and 250. You see, this is actually a very standard way how you solve the problem. As long as you see the question ask you for something big, something kind of like difficult, no worries, try to list them out. And hopefully you will be able to find out the pattern. So far, so good? Okay. This is actually a Canadian, but this is actually like American problem, right? I'm going to give you a Canadian problem, and which is pretty much the same thing. You're going to find, this American or Canadian problem, they're just basically copy one from each other, and all the strategies are exactly the same. So let's go to our question number 5. Let's have a look at this Canadian problem. Okay. Now we're looking at a problem that comes from 2018 format. It's a Waterloo format problem, question number 21. Okay, format is for grade number 11, right? Grade 11. But trust me, using all the strategies we have introduced, it is so easy for you to solve the problem. You don't have to wait to go to grade 11. You can solve the problem right away. So let's Let's read the problem first, and then I'll give you some time. Then try to tell me, how do you think? How? There's truly like two ways, right? Either the pattern or periodic. That's everything. The question says a sequence has terms a1, a2, a3, whatever. The first term is a1 equals to x, and the third term is a3 equals to y. Okay? The term of the sequence has the property that every term after the first term is equal to one less than the sum of the terms immediately before and after it. The value for this term is one less than the sum of the term immediately before and after it. Okay? And the question just worried if you do not understand this English sentence, he actually give you a mathematical explanation. That is, when n is greater or equal to 1, an plus 1 equals to an plus 1 minus 1. You see, that the Canadian problems are so nice, like the Canadian people. It just not only give you the English explanation, but also the mathematical explanation. Just try to make sure you can understand. Okay, you see, AMC won't give you this. AMC just give you one sentence, you understand it, that's it, and then just directly give you the problems. Okay, with all those information, the question asks you, what is the sum of the first 2018 terms in this sequence? Okay, the question is not asking the value for a 2018, it's the total sum of the first 2018 terms. Okay, I'll give you some time, think about it. I think two things, either there's a pattern, you can solve it very easily, or there is a periodic thing, right? Either of these two, either way, you will be able to help yourself determine the sum of first 2018 terms. So maybe I'll give you 2 minutes, think about it, and then we're gonna maybe ask somebody to give us some ideas. Please, I really want you guys to get involved in the process, since we do not have many since we do not have many students here. It is better that we can collaborate. Okay. Your first question is try to figure out this problem is a pattern problem or this problem is a periodic problem, right? And taking from there, let's try to solve the problem with more details. Think about it. What is the pattern? It's either way, right? If you figure out that, you're one step closer to the solution of this problem. Whoever figure out what it is, please signal me from the group chat. It's either a pattern or periodic. Who can tell me what is the pattern or what is the period? Which one is the solution for this problem? Need more time? Okay, no problem. Calculation is very important. Okay, in the bootcamp, we have no time for you guys to do any calculation, but in our regular knowledge-based lectures, I want you guys to get your hands dirty, do the calculation. Very important. All right, I see somebody already has the correct answer. Okay, I'm gonna be asking Stephen, what did you find?
I find that every 6 number of the sequence is a period.
Is that right? You see, it's either periodic or pattern. Yes, so for this guy, this is a periodic sequence. So what's the period? I'm just gonna give you the answer right away. A1 equals to x. A2 equals to x plus y plus 1, minus 1, right? A3 equals to y. You just keep writing A4 equals to 2 minus x. A5 equals to 3 minus x minus y. A6 equals to 2 minus y. A7 equals to x. A8 equals to x plus y minus 1. You see, all the way comes to here, you find out, okay, this is again a periodic sequence. But this time the period is a little bit long, it's 6. So don't give up. As long as you're calculating all the way to number 7 and number 8, you find a value, right? So the period t equals to 6. Right? Normally speaking, we use t to represent period. This is more like from functions naming convention. We use t to represent the period. Okay. So that being said, if the question asks you to determine what's the first S2018 is actually a lot of terms together, right? A1, A2, all the way to A2018. Say S2018 equals to A1, A2, all the way to A2018. But don't be panicked. Like I said, sometimes if you can't find out a solution right away globally, try to break it. Break it into small groups using the splitting, right? Still remember? This is what we mentioned in our at a very early phase of our lecture. So this function, this period, this sequence, excuse me, this sequence is actually a periodic sequence, right? Or this function is also a periodic function. So that being said, A1, A2, all the way to A6, this is going to be one period, right? A7, A8, all the way A12. That's going to be another period. All the way you go to, this is going to be A2016. So from A20 to A2010, I think 2011, right? 2011, all the way to A2016. This is going to be another period, right? These are all the period. Well, A26, 2017, A2018. Is that right? So that being said, what you need to do is you just need to calculate a period for one cycle, right? The sum of one period. And how many cycles you have here? You have 363 cycles. 363 cycles, right? So you just have to use 363 to time the value for one cycle. One cycle is actually 6, right? You add everything together, this is going to be 6. And you just have to figure out there are 363 cycles altogether, plus 2 leftovers. So these 2 leftovers, this one is going to be A1, this guy is going to be A2, right? Because they are basically repeating themselves. So what's the value for A1? X. What's the value for A2? X plus Y minus 1. So in total, what's the value? That's going to be your
2x plus y plus 2015.
That's perfect. 2x plus y plus 2015. Is that right? Do we have it? Yes, that's going to be our E part. You see, this is something quite understandable. Again, we're using exactly the same pattern. This is going to be periodic function. As long as you're dealing with periodic function, focus on one period, right? You figure out the value, the sum for one period, all the other following term is going to be repeating themselves again and again and again. Eventually, you repeat regardless how many periods, I don't really care. You just have to figure out the last 2 terms, right? Some leftovers, put it from there, you'll be able to solve the problem fairly quick. So far, so good? Perfect. You see, finding out a pattern is always important. You're going to use the pattern, try to solve all the problems. Okay, with all of this, let's go for another problem. Let's go for a relatively, I don't think it's very difficult, but it's a little bit like time confusing problem. It's a problem from, it's time consuming problem. It's a problem from 2015, AMC 10B, question number 24. Okay, it's pretty much like the last problem from AMC 10B. So this problem looks like a little bit, complicated, confusing, but as long as you really, down to the ground, list out first a couple of terms, find out a pattern, this problem can be very easy. There's nothing tricky for such a problem. So let's have a quick look at a problem altogether. The problem says, Aaron, the ant, walks on the coordinate plane according to the following rules. Okay? He started at orange, P0 equals to 0, 0, which is the orange, facing to the east and walks 1 unit. Okay? So he walks 1 unit, he will be arriving at P1 equals to 1, 0. Okay? For n equals to 1, 2, 3, right after arriving at a point Pn, if Aaron can turn 90 degrees left and walk 1 unit to an unvisited point, Pn plus 1, he will do it. Okay? As long as you get a place, if you can turn left 90 degrees and walk 1 unit, you can receive an unvisited point, a new point. Please do it. Otherwise, if you can't, let's say if you turn 90 degrees to the left, you walk 1 unit, you're not arriving at a new point, the point you have already visited. Okay? So that's the otherwise, right? He walks 1 unit straight ahead to reach Pn plus 1. So something like this. If at a certain point, the ant, Aaron, is already here, is facing to the east. His first option is try to turn 90 degrees. I'm going to use the color black. Turn 90 degrees to the left, walk 1 unit. If for this new point he has never ever visited, okay, that's it. He's going to do this. Or if this black point, let's say P, he has already visited, right? So he won't be able to do it. He won't be able to do that. He would just directly move forward because for now he's facing to the right, right? You just move forward 1 step to reach another point, P1 prime. Okay? So thus, the sequence of the points continues P1, P3, P4, P5. You can try to use the logic to basically write several terms based on that, and so on. So in a counterclockwise spiral pattern, okay, because they always turn left, this is going to be a counterclockwise spiral pattern. With all those information, the question asks you, what's going to be the value for P 2015? So that being said, after Aaron walk for 2015 steps, what is going to, not 2015 steps, after he remove, right? So every time he have go 1 step, go a new point, so on and so forth. After he do 2015, right? What is going to be the value for his P 2015? Of this value for 2015. Okay? He has to walk way more steps than 2015 in order to achieve such a point. But anyway, let's try to figure out what is going to be the coordinate for P 2015. So this problem, how are you going to deal with that? This is kind of like you have to follow, right? What is defined by this problem. Try to go 1 step, move left, another step, move left, so on and so forth, and try to figure out how this one works. So give you maybe 30 seconds, maybe give you 1 minute again. Try to think about it. Maybe you can't have the answer right away, but try to find out what is the solution for such a problem. Either there's a periodic thing or there's a pattern thing. It's either way, right? That's the only thing you can do for such a problem. Think about it, and then you can post those answers into the group chat. how can you find out either the pattern or period?
It's like 2, 4, 6, 8.
2, 4, 6, 8. Yes. Okay, that's a very nice observation. That's pretty much looks like the pattern, right? Okay, what else? Some other patterns? So for such a problem, you see, like this is going to be like not only like a number, right? You have to basically follow the ends, like kind of trace and figure out what a value comes from, right? So no problem. How to do such a problem? I think the most important thing is let's try to follow the end, right? Try to list out how those different steps looks like, and then hopefully taking from there, we will be able to solve the problem. Let's have a quick look how we're going to do with such a problem. So apparently you need to have kind of a coordinate, right? Let's try to find this coordinate. Okay, so at the very beginning, the end stands here facing to the east, right? You have P0. So according to the definition is it's going to go one step, go to P1. P1 will be 1, 0. Right? This is something quite understandable. And then, like I said, as long as you go to P1, your first option is try to turn left for 90 degrees. Use move on one step to see if you can get to a new point. In our case, of course, you will be able to come to here, P2, which is 1, 1. Okay? As long as you go to P2, 1, 1, the next one is you can see if you can turn left and use and move on 1 unit to see if you can reach a new point. You're going to come to here, right? You're going to come to here. And then moving forward, can you do one step forward? Yeah, in this moment, you actually have two choices. Either is you turn left 90 degrees. At this moment, you're facing here, right? If you turn left 90 degrees and move forward one step, if you reach a new point, just do it. Otherwise, you're going to move forward. Apparently, if you turn left 1 unit and move down for turn left 90 degrees and move down for 1 unit, you're going to reach P0. You have already visited, right? So therefore, you have no choice but moving forward. Okay? So this is actually your P3. This is actually P4, right? As long as you're done for P4, your next step is, again, if you turn left for 90 degrees and move forward for 1 unit, if you can receive a new one, please do it. In our case, no problem. You can come to here, P5, right? Now facing south. Again, if you turn left 90 degrees and then move 1 step forward, you're going to go back to P0. So you won't be able to do that. You have to move forward 1 step, reaching your P6. Okay? So like I said, there's nothing too complicated. You just basically follow the pattern, right? Even though for now you won't be able to see any like conclusion, any pattern. No worries. Let's try to do several. Okay? Take our time. Let's try to do several. Whenever you go to 6, if you turn left and move 1 step, you'll be able to receive a new point. This is your P7. Okay? Continue. P7, if you move left, and then if you turn left and move 1 degree, you're going to go back to P0. So you can't do that. You have to go here. P7, P8. Okay? Again, P8, if you turn left and move 1 step, you're going to go to P1. Of course, you won't do that. You're going to go to P9. As long as you go to P9, you can turn left, right? And move 1 step. Go to P10. And then go to P10. If you turn left, move one step, you're going to go back to P1. So you can't. You have to move forward. You see? Nothing really complicated. You just follow the pattern. But sometimes you can just basically do 1, 2, 3. You figure out a pattern. But this time you might do more in order to figure out a pattern. This one's going to be P11. As long as you go P11, if you turn left and then move one step, you're going to go back to P2. You can't do it. You have to move forward. You're going to go to P2, right? 2, 2. You can't keep doing that, right? The next one is going to go to here, go to here, go to here, go to here, right? And then you're going to go to here, go to here, go to here, go to here. This is going to be 13, 14, 15, 16, 17, 18, 19, P20, right? So all the way comes to here. Did you find out a pattern? This is kind of like a spiral, right? Every time this is getting bigger, 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 bigger. It's a big spiral.
It's kind of like the Fibonacci sequence.
Exactly. It has like a Fibonacci feeding, right? It has like a Fibonacci feeding. So that being said, it means what? It means this kind of things, there's a pattern, right? The question is asking what's going to happen for, what's the coordinate for P2015? P2015. I don't really know how to go to P2015, but let's have a quick look at it. How many steps you need to have in order to go to this, let's say, in order to go to here? Let's have a quick look at it. How many steps you need to get in order to go to, -1, -1, -2, -2? Every time this is kind of like a open spiral, right? Every time you need more steps to go to, maybe the other one was -3, -3. Let's try to find out a pattern. Like I said, you need to find out a pattern, right? All the problems are actually evaluated from the pattern. So it looks like in order to go to your -1, -1, you need 6 steps, right? T6 equals to -1, -1. In order to go to -2, -2, you need 20 steps. Okay? You need 20 steps. So that being said, if you can figure out what is the rationale behind it, 6 equals to what? 2 plus 4. 20 equals what? 2 plus 4 plus 8. Okay? 2 plus 4 plus 8. If we want to go for this is going to be 2 plus 4 plus 8 plus 10. Okay. This is kind of like a what? 30 steps. Did you guys find out a pattern? So that being said, as long as you want to reach at a minus k, -1, -1, -2, -2, -3, -3. If you want to go to -k, you probably want to go for 2 plus 4 plus, oh, excuse me. I think I got a typo here. This is 6, right? Yeah, this is my bad. This is, okay, 2 plus 4 plus 6 plus 8. Yes. Yeah. If you go to -1, -1 is 2 plus 4. If you go to -2, -2, it will be 2 plus 4 plus 6 plus 8. And if you want to go to -3, you're going to go to 2 plus 4 plus 8 plus 10 plus 12. That's going to be 20 plus 22, 42. So that being said, if you want to go to -k point, you're probably going to do 2 plus 4 plus 8 all the way go to 4k. Now, this pattern might not be so conspicuous, but if you're not so confident, you can basically list out more terms. Okay, you always do 2, 4, 8, 2, 4, 8, so on and so forth. All the way you're going to stop as 4k. Okay, So maybe I'm going to rewrite it here. Here, this is not very clear. 2, 6, 8. Okay, 2, 6, 8. You always do the 2, 4, 6, 8, 10, all the even numbers, all the way you go to 4K. All the way you go to 4K. So this is going to be 2, 4, 6, 8. This is going to be 2, 4, 6, 8, 10, 12. When you're going to stop? You're going to stop as long as you go to 4 times of this coordinate. You're going to stop whenever you go to 4 times of this coordinate. Okay? So that being said, if you keep doing this, how many steps you're going to write? All the way you go to this minus k position. 2, 4, 6, 8, 10, all the way to 4K. You're going to stop at 4K. So this is what? This is you're going to like a tiny arithmetic sequence related property. I think, yeah, we don't really cover the arithmetic sequence yet, but generally speaking, you got an idea, right? This is an arithmetic sequence. So this guy, if you add them together, it's going to be 2K, 2K plus 1. Okay, this is going to be 2K, 2K plus 1. You put everything together, and then you'll be able to figure out, okay, these are actually the total steps you need to walk in order to go to this minus K position. So far, so good? Can I have some feedbacks? Are we all on the same page?
Yep.
Yes. Okay, perfect. So this is going to be your minus K. Well, the question is not asking for minus K. The question is asking what's going to be the value for P 2015? What's the position after 2015 steps? I don't really know where this 2015 looks like, but let's do a very easy peasy calculation. We want to go for 2015, right? But I know that as long as you reach the minus K point, you have to go for 2K times 2K plus 1 total steps. If we let K equals to 22, you can find out 2 times 22, 2 times 22 plus 1. That's going to be 1980. Okay, 1980 is actually smaller than 2015. It means that as long as you already spent 1980 steps, okay, I'm going to do something like here, right? So you're going to do this kind of this, right? All the way. Okay, at a certain point, you come to here. You already write 1980 steps. Okay, you already go 1980 steps. And you are currently stopped at minus 22, right? You let K equals to 22, your position will be minus K. Okay, so all the way from there, what are you going to do? You're just going to keep writing to the right, right? Keep walking to the right. You just keep walking, all the way. What are you going to stop? All the way, you have to go to P23 minus 22. And then it's time for you to take another right turn, another left turn going up. Is that right? So that's the thing. You need to understand that this is always like something like this. Every time you do one forward, right? You do one more, come to here. You do one more, comes to here. If at one step, you already at minus 22, the next step, you want to turn left. It's going to be 23 minus 22. Is it right? You check the pattern from here? You check the pattern from here? Just like one step forward. So far, so good? One step forward. Okay. As long as you know that, let's have some quick discussion. So that being said, from this 1980 steps, you just keep writing, keep walking to the left, or keep walking to the right. Right. All the way, you're going to stop at 23 minus 22. So before you hit this 23, 22, you just keep writing to the right, right? There's nothing, you're going to change your direction. From 1980 to 2015, how many steps? There are only 35 steps. But the next time you want to really take a left, it's going to be 22 plus 23, 45 steps away. Is it right? After
Yeah.
45 steps, you're going to turn left. So that means what? From
The
this
point is
moment,
on this line.
is it right? Just like Stephen mentioned. From this moment, you're going to keep walking to the right until you hit your P20 15 step. You're not going to change direction. You just keep straight to the right, all the way you hit P20 15 step. You're only going to take turns after 46 steps. That's 10 steps away. So don't worry about it. So at this moment, you are at minus 22, minus 22. You just move to the right for another 35 steps, right? 35 comes from 20, 15 minus 1, like 1980. So this plus 35, your y coordinate are still the same, minus 22. So that's going to give you the answer, 13 minus 22. Do we have it? 13 minus 22?
I think it's D, right?
It's, yeah, 13 minus 22.
Yeah.
That's the D bar, 13 minus 22, right? You see? This problem might be a little bit difficult than our previous problems, but the thinking process are exactly the same. You have to list out several terms and find out a pattern, right? This is not a periodic function, unfortunately, but this is like a pattern. So the pattern might not be very conspicuous, but as long as you're not so confident, list out more terms. If you're not so happy with minus 3, maybe try minus 4, even minus 5, you will be able to sooner or later get a pattern. As long as you get a pattern, you'll be able to solve the problem fairly quick. So far, so good. A student got a question of why 2k times 2k plus 1? This is the arithmetic sequence. Try to determine the first k-term sum of the arithmetic sequence, a1 plus an divided by 2 times n. If you're not so familiar with that, no worries. We'll talk about it in our arithmetic sequence term. This is only a tiny thing, but generally speaking, the thinking process is very linear, right? So you see, just using the pattern, you don't have to do a very complicated calculation, very rigorous calculation. Guess out from the pattern, and you will be able to solve the problem fairly quick. So far, so good? Okay, perfect. That's actually our lecture number 1. See, our lecture number is fairly easy. We're not talking something too complicated. We just try to figure out how to use the pattern to solve the problem. Trust me, 99% of the AMC problem, they just need you to find out a pattern. That all the sequence related problem, you just need to find out a pattern. Either the pattern is more like from a certain formula, a certain pattern, like we see most of the time, or the pattern will be a simple periodic function. As long as the periodic function is actually easier, right? You just find all the periodic property and find out your final term actually falls into a reach term in this period, and you'll be able to get it resolved. All right, I think that's pretty much what I want to say for our today's lecture, lecture number 1. So hopefully you guys got a rough idea how the sequence related problem, you're gonna open your thinking, right? Open your thinking process, that's the direction. In our next lecture, we're gonna give you guys more flowery problem. Again, we're going to do some, these are the basic sequence related problem, but there will be way more analysis, some more difficult problem, and you're going to see more analysis, try to capture the pattern. And taking from there, we'll see more interesting strategies, try to solve some relatively difficult problem. All right, I think that's pretty much what I want to say for today's lecture. And later, I'm going to upload our assignment into our Google Classroom. You have 1 week to finish the assignment. As long as you're done, I'm going to be able to help you to grade it. And I'll be asking the student who did a good job to give us a quick presentation, try to show us how you think for the problem for the very beginning of our next lecture. All right, I think that's pretty much for today's lecture. You have any questions for me?
What is the Google Classroom code?
I'll talk to you offline. Okay?
Okay.
All right. If all good, I wish you guys a good day. I'll touch base. And for
Bye.
the next Monday.
Right. Can I also have
Thank you.
the Google Classroom code? I don't have it.
Yeah, you can talk to me, and
Thank you.
then maybe ask your parents to talk to me. I'll be able to send you the code.
All right,
Okay.
I'll tell them. Thank you.
Perfect. Thank you. Mhm. Have a good one. Bye, guys.